everyone. Today we are starting with a new topic, that is chemical equilibrium. Okay, and to start with the chemical equilibrium, first of all, you should understand the basic reactions, the basic chemical reactions that we have. All right, there can be two kinds of reactions. One, are the ones which are irreversible. This is something that we have discussed before. We have irreversible reactions which go in directly in just one direction, right? But then there may be a chance that sometimes these products can be reverted back into the reactants. That is a condition of reversing. So that is a condition of reversibility. So if we term these as the irreversible reactions, we term these as the irreversible reactions, there is also a chance that we can probably reverse them, because if this and this can actually lead to the formation of C plus D, there is also a chance that this C plus D can also revert back to the formation of A plus D. That now depends on how spontaneous the reaction is and what is the condition. Say if one of them is a gas, it will escape to the atmosphere. Then you will not have the subsequent conditions to actually get it back also. So there are many factors which decide whether a particular reaction will be reversible or not reversible, right? This is like irreversible reaction. But when we talk about the reversible reactions, if I have to remove this ir from here, then it will be represented by this symbol, something that you have done before. So these are the conditions where you have the reversible reactions. And while doing the previous topics of chemistry, we've already discussed that in this case, the rate of the forward reaction is equal to the rate of the backward reaction. And another thing is, like we also state that reversible reactions are those in which the force which is employed for the forward reaction is infinitesimally greater than the force which is required for the backward direction. Now, see, when I talk about reversible reactions, I can also talk about the condition of equilibrium. Right, so this is what we are going to do now. From now on, discuss the conditions of various things which are related to the equilibrium, especially when you talk about the chemical reactions. Then we start talking about the chemical equilibrium. Now here, remember that when we talk about the concentration of, you have the reactants and the products. The concentration what we have is of the reactants and the products at the equilibrium is known as the reaction equilibrium mixture. It is known as the reaction equilibrium mixture because that is what the concentration is, that of the reactants and the products at the stage of equilibrium. Another important feature that I am telling you is that here the rate of forward reaction will be equal to the rate of backward reaction. Now in order for that, let me just first explain what do you mean by the rate of a reaction. Say if I have to talk about the rate of a reaction, then in that case, say let me talk about the irreversible reaction first. I want your attention onto the board, all of you. Now if I talk about any reversible reaction, first of all, say this is giving my products, let me just talk about only reversible reactions right now. If this is my reaction, fine, then my rate is what? It is the rate of change of, rate is always with respect to, it will always be with respect to time. Rate means what? It is the speed at which your products are getting formed or reactants are getting consumed. So in that case, the rate is generally given by a formula that you will be doing in detail in next year. And you know that the study which deals with the rates of the reactions is known as chemical, it is known as chemical kinetics. The study, the branch of science that deals with the rates of the reactions is known as chemical kinetics. Now what do you understand by rate? It is like for the reactants, you know, they are getting reduced with time. So that means if I have a normal reaction, say I just changed this to reactants giving products. You understand this? Reactants giving products. So now I know that my reactants are getting reduced with time. So I put a minus sign to show that they are getting reduced. So the change in concentration of the reactants, the change in concentration will be like if R is the, say if you have initial concentration as Ri and after some stage it becomes Rf after time, say at time T1 your initial concentration of reactant is Ri, at time T2 say the initial concentration, so say the final concentration is RF, then you know what will be the rate of the reaction. It will be RF minus RI upon T2 minus T1, right? That is what the rate will be. Rate will be RF minus RI upon T2 minus T1. If this change in concentration is infinitesimally small, we talk about in terms of differentials. So then I am putting a minus sign because the reactant concentration is reducing. So what I'll have here is minus dr by dt. Okay? That is minus dr by dt. And what will happen for the products? Say if product concentration initially it would have been 0. Initially it would have been 0 only, but let's call it, say if I start at a particular time t1, I'd forget to note it down initially that as to what it was, or if I have the data for 2 time intervals. So at time t1, say if it is pi, and at a final temperature, say it is at pf. So what will be the change? Again, it will be, my rate can also be defined as pf minus pi upon t2 minus t1, but in this case your product concentration is increasing with time. So here you can put your expression as, you can also put this expression as plus dp by dt. This is known as the instantaneous rate of the reaction. Now rate, I am telling again, rate is the speed at which your reaction is proceeding. It talks about the difference in the change in the concentration of either of the reactants or the products with respect to time. Okay? And then you note that because reactants are reducing with time, by convention we put a minus sign here, which shows that your reactant is getting consumed in the reaction and your product is getting formed. So you have plus dp by dt as the rate for rate of the reaction. So the rate of the reaction, both of them are same. Now if I replace this with another reaction, say AA plus BB is giving CC plus DD. If this is the reaction, now in this case, let me tell you, here the rate will be equal to minus dA, the concentration of one of the reactants, by dt, and that will be divided by its respective stoichiometric coefficient. That will be equal to minus 1a dA by dt. Clear with that? Each of these expressions that I have written will be divided by their respective stoichiometric coefficients. So now what about this? What will it be? It is also a reactant. It will be minus 1 by B by dt, and what about the products? Now it will be plus products and they are getting formed in the reaction. D. Now write it down quickly. You should also be able to write it down in your own words. Say if I talk about any reaction, CH4 plus O2 giving CO2 plus H2O. So then in that 2H2O and 2O2, right? Write down the rates of this reaction as well. Just write down the instantaneous rate expressions for each of these reactions. Clear to everyone as to how to go about doing it? It's simple. It is always compare. It is like change in the concentration, either the reactants or the products with respect to time. And if it is rate, you put a minus sign. If it is products, you put a plus sign, because reactants are getting consumed and products are getting formed. Done for this question also. Now for this, what will we have the rate as? The rate will be equal to minus the concentration of methane upon dt. What will this be? Minus 1 by 2 now, O2 upon dt, and this will be plus dCO2 upon dt, and this will be plus 1 by 2 d concentration of water upon dt. So it is very important right from now on that you balance your reactions and then arrive at any expressions that you require in either kinetics or in equilibrium. Okay, now what we are saying is that if any reaction is in equilibrium, then the rate of forward reaction is equal to the rate of backward reaction. This is what we are talking about. Okay, so after having done this, now let's start discussions about the equilibrium states only. In the equilibrium states, when there is no change, further change, we've already discussed this, that we have different types of equilibrium that we discussed in thermodynamics. What were those? We discussed the mechanical equilibrium, then we discussed the thermal equilibrium. Another one was the chemical equilibrium. Now chemical equilibrium is the one in which there is no further change in the compositions at a particular temperature. So here when we talk about it, say when we talk about the states of chemical equilibrium, it can be of three types. Okay, one state can be when your reaction has proceeded near to completion and then it attained equilibrium. So that means in that the products are present in very high concentration. There can be another stage. Now here the first one can be put up when the reaction proceeds completion. Alright, you can just write the three types. One is when your reaction precedes completion. The next is when your reaction say in which only a small amount of product is formed. So it has just, reaction has just got initiated, This can be another form. And the other one is in which the reaction is the one in which the concentration of reactants is equal to the concentration of the reactants is equal to the concentration of products. Now these are the three kinds that we can actually discuss in detail also by studying their quantitative relationships. Remember, one of the states that we are talking about is when the reaction precedes completion. Completion means that your products are now in higher concentration, but now it has come to a state where there is no further change in the composition. Whatever products have been formed and whatever reactants have been utilized are now stagnant. So in that the reaction is proceeded to completion. Do you get that? Otherwise you get a picture that if products have formed majority in major amount, then in that case you call it a forward reaction. No. I am saying that the equilibrium can still be attained when your reaction has proceeded near to completion, or maybe you just started up with the reaction, alright, and like for the case of weak electrolytes like acetic acid, it's very feebly ionized, very little concentration of your ionized form is there, whereas the rest of it remains in the unionized form. I hope you remember that this we have discussed before. All these reactions, what we have is, say in this case you can say that this is a very weak electrolyte, so the dissociation concentration is like very low and you have majority of it in the unionized form. So there can be examples where the reaction has just got initiated and then attained equilibrium, where now there is no further change in composition. Or there can be an appreciable amount of concentrations of the reactants as well as products, where the reaction you can say reached some intermediate state and then attained equilibrium. Now when we talk about the equilibriums of ions in solution, there is another branch of science that we will talk about in detail later, that is called ionic equilibrium. When we talk about the equilibrium of ions in solution, then we talk about ionic equilibrium. So we will be talking about the ionic equilibrium as well. Now just put down a reaction where you have say phase transformations. We can talk about the now important things, that when you talk about the equilibrium can exist in various kinds of phase transformations. So let me just take up the most simple example. Like for example, if we have water in the liquid form and we put it in a closed container, of course some of it may vaporize and form water vapor. So they may attain a state when you will have the water liquid in, or let's talk about the first one, that is like you can also have solid in equilibrium with liquid, and let's take up the example of water. and you can also have liquid in equilibrium with vapor, where we can again talk about water. So remember that when you have the water in the solid form, then you can say that ice is in equilibrium with water. Here in this case, what basically happens is your ice and water in equilibrium means that it doesn't mean that once your ice and water are in equilibrium, the ice will remain with the same kind of molecules that it originally had. See, H2O is there. All the H2O molecules are indistinguishable, but you have so many molecules in one particular structure of ice that you have. Right? Now what I want to state here is that when your ice is in equilibrium with water, that is the state where you will say there will be no further change in the composition, but your water molecules will keep sticking to the ice, and more other molecules of water may be coming out of ice to go into the liquid state. You getting that point? This means that what we are talking about throughout in chemical equilibrium, it's a state of dynamic equilibrium. Dynamic equilibrium. Say if I talk about that my hand is in equilibrium with this stand, then in that case I'll say it's a static equilibrium. Why? Because there is no exchange in between the two. Whereas when I'm talking about the equilibrium between ice and water or any other state, here in this case I'll talk about the equilibrium of water with water vapor. If I take up the example here, it will be water in equilibrium with water vapor. So again here you will have more and more of water vapor, water molecules getting converted into water vapor, and because your water vapor is in the vaporized state, it will keep colliding with the walls of the container and then keep condensing back to the water molecules. So that exchange is continuous. So it is not a static equilibrium, but it is a dynamic equilibrium. Why? Because the exchange of molecules keep happening. Got that point? So this is very important for you to understand. The temperature at which we generally say that the water actually forms ice is known as the normal freezing point. And here when we actually say that when the vapor pressure becomes equal to the atmospheric pressure, what you get is the boiling point. Right? So we talk about the freezing point here, which you know all know very well. Freezing point is that point where you have the basically it's like related to the pressure factor, which are like equivalent. So here you say that when your water actually gets converted into ice, you call it the freezing point, and when your vapor pressure becomes equivalent to the atmospheric pressure, then you call it the boiling point. Another thing is that you can actually state that water and water vapor, when they are in equilibrium at the atmospheric pressure, then in that case also you say that the boiling point is achieved. And it is generally believed at higher altitudes the boiling point decreases. Please make it a point to write down, because this question is put in many forms. At higher altitudes, you generally have the boiling point decreasing. Why is that so? Because there what you have is the boiling point decreases. That is because the temperature which is required to make your vapor pressure become equal to the atmospheric pressure is very low. Because the atmospheric pressure, if it is low at higher altitudes, then you see that now the difference in the vapor pressure and the atmospheric pressure may not be that high. So then you need only a little bit of temperature, and if you need a little temperature, that means the boiling point has lowered. So that is one another factor that we can talk about. Then the third of the phase transformation can be, we have talked about the conversion of solid to liquid, liquid to vapor. The third which is possible is the solid vapor equilibrium. The solid vapor equilibrium, in which you can just get to know some examples. These can be those in which your solid is directly subliming to get formed into a vapor state. There you can just take up an example of iodine vapors. So when you put iodine in a particular container, if it is transparent, you can clearly see that, you will see that after some time there will be an increase in violet coloration. And that coloration will actually be stagnant after some time, which means that the equilibrium has now been attained between iodine in the solid form and iodine in the vapor form. So you can have some examples similarly for that. You have iodine in solid getting in iodine in vapor. Then you can have the example that of camphor also, camphor in the solid form, and you can have example of ammonium chloride also with sublimes. These are just examples of the phase transformations that we can talk about. And each of these you can have some or the other way of measuring whether the equilibrium has been attained or not. Like for the case of water and water vapor, we can always talk about the pressure measurements also. There we can talk about when the pressure is no more, it's not changing any further, you say that the equilibrium is attained. Then the next case, we can talk about the equilibrium involving dissolution processes. Dissolution processes. Now here again, when we talk about equilibrium involving dissolution processes, that means we can talk about the dissolution of, say, solid in liquid, or we can talk about the dissolution of gases in liquids also. Gases in liquids. Now when we talk about the dissolution of solid in liquid is something that you must have tried so many times before. And what is that? When you actually dissolve your solid into liquid, there you have like sugar in water. You know that after a certain amount of time, you have that no more sugar dissolves. But if you heat it again, then again you can get, if you heat the solution again, then again you can get the saturated solution. I mean, you can add more sugar. If you add sugar to water at a normal temperature, you know that there will be a point when no more sugar will dissolve. So you say that the solution has become saturated. Now if you heat it again, then you know you can add more. So in order to define a saturated solution, it is important that you define your temperature also. So saturated solution is the maximum amount of solute that can be added in 100 grams of solvent at a particular temperature. At a particular temperature, and remember that this also depends on, it is dependent upon temperature. By and large, I have told you that all physical parameters depend on temperature. So this is one thing. So here in this case, you can talk about saturated solution, or this is the point where the rate of dissolution of sugar, where the rate of dissolution of the solid is equal to the rate of crystallization of the solid. Because the moment you get one speck extra of the sugar which is not getting dissolved, you say that the saturation point has been achieved. So this is the point where the rate of dissolution is equal to the rate of crystallization. And how can you actually check? This can be checked, you know, you can add say radioactive sugar. Alright, and then by making use of radioactive sugar, you can actually check what is the rate of radioactivity. Once that becomes in equilibrium, then you state that the dissolution process has now attained equilibrium, because the rate of dissolution is equal to the rate of crystallization. So this is another kind of an equilibrium in the dissolution process. Now for the gases, when you talk about in liquids, let me tell you that when gases are dissolved in liquids, you know that they will be dissolved under a certain kind of a pressure. And then if you have the gases getting dissolved in liquid, simultaneously the liquid is also vaporizing. The liquid is also, so there will be some kind of a vapor pressure also above the liquid. So when that vapor pressure is that has attained equilibrium. You know how the liquid and gases attain equilibrium amongst themselves. It's a state of dynamic equilibrium where your liquid molecules will keep vaporizing and your vapor will start coming back into the liquid state again. So that is the point. Here there is an important law that you need to remember, and that is known as the Henry's law. This law states that, first understand the law, that the mass of the solute which is dissolved in a particular liquid, see, mass of the solute, and what is your solute in this case? Gases. Whatever is lower in quantity, you call it the solute, and whatever is larger in quantity, you call it the solvent. So when I am saying that, when the mass, here Henry's law states that the mass of the gas which is dissolved in a liquid is directly proportional to the pressure of the liquid above it. It is directly proportional to the, I repeat, note down the Henry's law. Henry's law states that the mass of the gas dissolved in a liquid is directly proportional to the vapor pressure of the gas above it. Alright, so then you have M is equal to K into P. That is directly proportional to the pressure which exists in of the gas above it, which is in equilibrium with the liquid. I repeat, Henry's law states that the mass of the gas which is dissolved in a liquid is directly proportional to the vapor pressure of the gas which is in equilibrium with the liquid. Okay, so till now we have talked about the chemical equilibrium and the rates. I repeat, whatever we've done till now, we have just talked about. For all those of you who've just come now, we have started with the topic of chemical equilibrium, and in chemical equilibrium, what we basically have is like, we have the chemical reactions which by and large exist in equilibrium with one another. When we talk about them, we can talk about different states at which the equilibrium can be attained. One is when the reaction has proceeded near completion, right? Or when the reaction has just started and it attained the equilibrium. So your reactants remain in majority of the amount and products are in little amount. And the first case that I talked about, the products are in larger amount and reactants are in little amount. And the third one is an intermediate state where you have the concentration of the reactants to be equal to the concentration of the products in fairly good amounts. Then the basic funda of the chemical equilibrium is that the rate of forward reaction will be equal to the rate of backward reaction. This is very important. Then you should know how to write down the rate of a reaction. The rate of the reaction can be the change in the concentration of either the reactants or the products upon the change in time, right? And then what we have is, then we talk about the different kind of equilibrium which exists in the transformations. Say you have what kind of transformations, phase transformations can you talk about? Solid to liquid, where what becomes important is the equilibrium is attained generally at the freezing point, right? For liquid to vapor, the equilibrium is attained at the boiling point. And for boiling point, you have many questions related to it, because you have to attain that you have to understand that the boiling point is attained when the vapor pressure of the liquid becomes equal to the atmospheric pressure. And so at higher altitudes, we generally say that the boiling point reduces. The third types of phase transformation that we've just talked about is the solid in equilibrium with the vapor. There you know that the vapor state will generally have no more change in the composition in comparison to the one which is occurring in solid, and these will be generally for those solids with sublime, because here you talk about the sublimation temperature or the sublimation point. So the equilibrium is attained basically at those margins where you have the conversion of one form into another. So you say that the state of equilibrium is attained. Another thing that we did talk about is the dissolution processes. What you had in the dissolution process, first we can talk of solid dissolving in liquid, where you say that the rate of dissolution is equal to the rate of crystallization, because you know that the saturated solution will be formed at that state. It will depend upon temperature again. It will depend upon temperature. Then the next thing that we talked about is the dissolution of gases in liquid. When we say that the vapor pressure of the gas is in equilibrium with the liquid form, right? And that defines your Henry's law, which states that the mass of the gas is directly proportional to the vapor pressure of the gas above it, which is in equilibrium with the liquid. So this is your Henry's law. So this is by and large what we've done till now. So now when we define the chemical equilibrium, look up all of you all. Now a chemical equilibrium, what you have is, there is a law that can actually help you find out the rate constant here. Alright. In this case, this is also known as the law of mass action. This law that I am going to talk about is also known as the law of mass action, as it was given by Goldberg and Vajay. In this case, it states that the equilibrium constant can be defined as the product, it can be defined as the ratio of the products of the concentration of the products upon the product of the concentration of the reactants, each raised to their respective stoichiometric coefficient. So in this case it will be Cc d to the power d, a to the power small a, and b to the power small b. So this is very important, this is a very important law where you need to understand. It is also known as the law of chemical equilibrium, or the law of, it is also known as the law of chemical equilibrium, or it is known as the law of mass action. It just states that the equilibrium constant is nothing but it is the ratio of the product of the concentrations of the products upon to the concentration, or to this product of the concentrations of the reactants, each raised to their respective stoichiometric coefficient. So that's like easy to remember. So just try and write down the first question for the day that I'm giving you is try and write down the equilibrium constant for this reaction. It's a very simple reaction. Write down the equilibrium constant Kc for this particular reaction. So in this case, how will you write down Kc? Kc will be equal to the concentration of the product to the power 2 upon concentration of H2 into concentration of I2. So in numericals, say if you are given just the values of Hi, H2 and I2, you can easily tackle them and can find out Kc. Okay, now remember, if I talk about the reverse reaction, alright, say if I am talking about the reverse reaction, then what will be the Kc dash? Now call it Kc dash. 2Hi giving H2 plus I2. So what will happen in this case? Now in this case, you will have your Kc to be equal to Hi H2 into I2 upon
Hi to the power 2.
it will be H2 into I2 whole to the power upon Hi square, right? And this is nothing but when you relate this Kc, say let this Kc be Kc dash, this Kc dash will be equal to 1 upon your original Kc. So remember that when you are talking about the reversal of the reaction, then in that case you are talking about the inversion of the equilibrium constant. I repeat it again. When you invert the reaction, then your Kc will be actually the reciprocal for the new form. Say now if you take the same reaction, if I talk about the same reaction, one thing that is done is if I talk about H2 plus I2, this is the reaction that we had just taken up. What was it? It was giving you 2Hi. You had seen that the normal Kc is equal to Hi square upon H2 into I2, right? Now when I just reversed the reaction, it became let the new constants be called as K dash. H2 plus I2 is giving, the reverse is what? Yes, it will change. When you have 2Hi, we'll just see if 2Hi is equal to H2 plus I2, then in that case I know that my new K dash or the equilibrium constant becomes equal to 1 upon Kc now. Now the question is, if we change the respective stoichiometric coefficients, will Kc change? Let's check it out. Now let's divide this reaction. Let's divide this reaction with 2. Alright. So then what does it become? Half of H2 plus half of I2. This gives Hi. Alright. So in this case your K dash will be equal to your Kc, it will be Kc to the power of 1 by 2. It will be Kc to the power of 1 by 2. Is that okay? You can check it for yourself. Now this will be Hi upon H2 to the power half, I2 to the power half. That means this is nothing but this entire Kc to the power half. right? And if I say multiply this reaction now with 2, if I multiply this reaction with 2, then what do I get? I get 2H2 plus 2I2, that will be giving me 4HI now. So in that case, what does my K dash become now? Now K dash will be equal to Kc square. You can check it out for yourself. What will be the equilibrium constant now? That will be equal to Hi to the power 4, which is Hi square to the power 2 upon H2 to the power 2, I2 to the power 2. So remember that whenever your reaction is reversed, your Kc becomes the reciprocal of the original equilibrium constant. Whenever it is multiplied by a factor of n, your Kc becomes equal to n into n times the equilibrium constant. Whenever it is divided, then your Kc becomes to the power n, and when it is divided by 2, it becomes the nth root of your original Kc. I repeat what I just stated, that if in case you are taking a general reaction, say AA plus BB is giving CC plus DD. If I am saying this reaction possesses an equilibrium constant Kc, okay, then if I am reversing the reaction Cc plus Dd in equilibrium with AA plus BB, then I am reversing the reaction, so the new equilibrium constant will be 1 by Kc, right? If I am multiplying this reaction with NAA plus n times, I am just multiplying this reaction with n, then my equilibrium constant will now be Kc to the power n. And if I am dividing it by n, then in that case my new Kc or the new equilibrium constant is nothing but Kc to the power of 1 by n, or you say it is the nth root of Kc. This is like the generalized form that you need to understand, because earlier in thermodynamics we were multiplying and dividing the delta H value accordingly. But here for the equilibrium constant, by the meaning of it that comes from the law of chemical equilibrium, you need to understand that the basic reaction will give you the equilibrium constant according to the law of equilibrium. C into D upon A into B, whole each of them is raised to their respective stoichiometric coefficient. When you reverse the reaction, you have 1 upon Kc as the equilibrium constant. When you actually multiply it with n, then it will be to the power n. When you divide it by n, it will be the nth root of the equilibrium constant. Okay, take up a question for this. I have picked up very simple questions from your book only, because it's just the first class. Get the hang of it, be comfortable. It's an easy topic where you have to do nothing but just to understand the equilibrium constant properly, and that you've already done. So now for the formation of ammonia, just write down the question. For the formation of ammonia from N2 and H2, for the formation of ammonia from N2 and H2, where the concentration of N2 is given as 1.5 into 10 to the power minus 2 molar, concentration of H2 is given as 3.0 into 10 to the power minus 2 molar, and concentration of ammonia is given as 1.2 into 10 to the power minus 2 molar. Find out the equilibrium constant Kc. Find out the equilibrium constant Kc. First of all, your basic purpose is to write down the equation. Write it down. What will that be? That will be N2 plus H2 in equilibrium with ammonia. Balance the reaction. It can be done simply, right? So you know that your Kc will be equal to NH3 whole square divided by concentration of N2 into concentration of H2 to the power 3. So just put the concentration terms here, and what will you have is, so you will have, quickly find it out and tell me the power. Do it in your heart. All right. Now an important question. Done with the calculations? Quickly do it. Shouldn't take so much time. They are just the simple calculations. For the next question, I take another question. At equilibrium, you have the concentration of N2. Remember one very important thing, that when you are applying, remember this important thing, that when you are applying the law of chemical equilibrium, keep working. When you are applying the law of chemical equilibrium, remember that all these concentrations that you are putting are the concentrations at the equilibrium only. These concentrations will always be at equilibrium, not at the initial state or not at the final state, where final state is generally the equilibrium state, but these will not be the initial concentrations ever. So I have put down the correct answer for this. One important thing that comes here is, now your Kc is turning out to be 1.06 into 10 to the power 3. What will be the units of Kc? The units of Kc will be according to these concentration terms only. What is this? This is the concentration maybe in molar here, or it can be any other unit that is given to you. So what will that be? That will be equal to the concentration square upon concentration into concentration cube. So the net will be, it will be concentration to the power minus 2, because it will be 2 minus 4. So it is a ratio of the concentrations according to the each of the stoichiometric coefficients that you have. So in each of these cases, the equilibrium constant may not just be without units. A constant doesn't mean that it will not carry any units. A constant will have units, and it will depend upon what factors do you have which are involved in calculating that constant. Like you have the universal gas constant. What is the universal gas constant? That is 8.314. That is 8.314 joules per Kelvin per mole. You know it's a constant, but it has units, right? So equilibrium constant will also have units depending upon what concentration terms are involved in it. So each of the equilibrium constant will be different for different reactions. Okay, then take down the next question. At equilibrium, the concentration of N2 is given as 3 into 10 to the power minus 3 molar. Concentration of O2 is given as 4.2 into 10 to the power minus 3 molar, and concentration of NO is given as 2.8 into 10 to the power minus 3 molar. I am writing down these concentrations again. N2 is equal to 3 into 10 to the power minus 3 molar. O2 is equal to 4.2 into 10 to the power minus 3 molar, and NO is equal to 2.8 into 10 to the power minus 3 molar. The reaction is carried out and has attained equilibrium in a sealed vessel at 800 Kelvin. What is the Kc for this reaction? In this reaction, remember, temperature is just given so that you know that the reaction has been achieved at this temperature. The equilibrium has been achieved at this temperature. The Kc for this reaction will now be equal to, now Kc for which reaction? You have the reaction as N2 plus O2 giving 2NO, all of which are in the gaseous form. So you will have Kc is equal to NO square upon N2. Then now it's like easy once you write down the reaction, and just calculate it and tell me what will it be. Simple. This is again very simple. You just have to simply substitute the values. Make sure that you know how to write down the equilibrium constant properly, because once you're able to write down the equilibrium constant properly, then that means the entire chapter will be like very easy to understand. Now I put down one last question for practice. PCl5, PCl3 and Cl2. Tell me the answer. The answer will be somewhere around 0.622 is what is given. what we have for Kc is equal to, now for the next question, PCl5, PCl3 and Cl2 are at equilibrium at 500 Kelvin, okay? They are at equilibrium at 500 Kelvin and having concentrations of 1.59 molar, 1.59 molar and 1.59 molar for PCl3, 1.59 molar for Cl2 and 1.41 molar for PCl5. Then find out the Kc for the reverse reaction of PCl5 giving PCl3 plus Cl2. Find out the Kc. There are two ways. First you find out the Kc of this or invert it, or directly you write down the reverse reaction and then give it. Okay. First I also give you a question. Okay, first find out Kc and then give the Kc for the reverse reaction. Kc for PCl3 plus Cl2 giving PCl5. Here Kc will be equal to PCl5 upon PCl3 into Cl2. Nothing could have been easier than this. This is like a simple, very simple reaction. So here, oh sorry, it's just the reverse. The reaction, the product of the product concentration first upon PCl5. This will be for the general reaction that is given. So you could have had this very simply. So that will be equal to 1.59 whole square upon 1.41. That will be equal to 1.79. This is coming out to be equal to 1.79, and now the Kc for the reverse reaction you know will be equal to 1 upon 1.79, and you can easily calculate that. Done? So this is like a simple thing that you can remember, that for the reactions at equilibrium, when your reactants and products both have attained equilibrium and you know their concentrations, then you can easily define the equilibrium constant, which is given by the law of chemical equilibrium, which is nothing but states that your Kc is equal to the ratio of the products of the concentration of the products to the product of the concentration of the reactants, each of which is raised to their respective stoichiometric coefficient. So Kc can be very easily found. The only now important things that I am revising for you is, if you have a normal Kc for a given reaction, if you reverse the reaction it will be 1 upon Kc. If you multiply the reaction with n, your new equilibrium constant will be Kc to the power n, and if you take divided by n, it will be the nth root, okay, of Kc. So you can do questions based on it accordingly. Now here we can also talk about, now we are talking about chemical equilibrium. There are two types of equilibrium that we can discuss. One is the case when we have the homogeneous equilibrium. Understand that homogeneous equilibrium state is that in which the reactants and products, all the reactants and all the products are in the same phase. All the reactants and products are in the same phase. I can just give you an example for that. The case of ammonia was an example where you have the N2 in the gaseous form, H2 also in the gaseous form, and it was forming your ammonia, which was again a gas. So you will have one is, this is an example of the homogeneous equilibrium. You can have another equilibrium where you have all the states in the liquid form. Say you can have an ester C2, CH3, CO, C2H5, an ester reacting with water, alright, to give acetic acid plus alcohol, to give acetic acid plus an alcohol. So here again you have all of them in the liquid state, so that is why you say that this is also a case of homogeneous equilibrium. Then you will have a case of heterogeneous equilibrium where you know that the state of the reactants as well as the products will not be the same. Even if one of the reactants or one of the products is in a different state, you say that this is like a case of heterogeneous equilibrium. Like for example, I can just talk about any reaction where you have say C solid plus O2 gas is giving you CO2. Alright, that's like CO2 in the gaseous form. So in this case you have one of them as solids. I've just taken up a weird example. Done? So now after talking about homogeneous and heterogeneous equilibria, there's another important thing that we can actually talk about right here itself. I'll come back to the heterogeneous equilibria, but there's something important that whenever you have anything in the gaseous form and when you talk about the ideal gases, you know that whenever you talk about the ideal gases, you talk about which equation? Ideal gas law equation. What is that? PV is equal to nRT. You know that your ideal gas law equation is equal to PV is equal to nRT. So that means your pressure is equal to some kind of N by V into RT, where N is the number of moles and if say V is the volume in liters, then you have this as the concentration in molarity, the way I told you. Number of moles per liter of the volume is your molarity only. So that means that is like a concentration term. So that means your pressure can be equal to CRT. That means the concentration term into RT, right? So now if I talk about any reaction, say from here I can just state that one thing that is important is you can realize that pressure is directly proportional to the concentration, right? So now if I actually take up a reaction like H2 gas plus I2 gas is giving 2HI, then I can write down my Kc. Kc is easy. This you have written so many times. This was the first reaction I wrote on the board. So you know it will be Hi square upon H2 into I2. Okay? Similarly, I can also write down the equilibrium constant in terms of pressures of the gas, and that I will call it as Kp, because here for the equilibrium constant I am referring to the concentration, so I am writing Kc. Here I am referring to the equilibrium constant in terms of pressure, so I am writing it as Kp. So your Kp is the equilibrium constant when I am talking about the ratio of the concentrations according to the pressure. This also follows the law of equilibrium. That means here Kp will be the ratio of the pressures of the products upon the ratio of the products of the pressures of the products upon the product of the pressure of the reactants, each raised to their respective stoichiometric coefficient. What I mean to say is your Kp will now be equal to the pressure of the product. So it will be the, had I got another product, I would have written the product of this with that. Alright. So P of Hi square now, because each has to be raised to their respective stoichiometric coefficient also. So this will be a PH2 into PI2. This is simply your Kp. Got it? Very simple. Now, each of your pressure is equal to the concentration term into RT. Because if I consider my gas to be an ideal one, that will be equal to concentration into RT. What is my concentration? Now, what will be my P of Hi then? P of Hi will be the concentration of Hi, right? Into RT, and this entire pressure is to the power 2. So that means this is Hi square into RT square. Okay? Then my pressure of H2 will be what? It will be the concentration of H2 into RT. The reaction is at a particular temperature. All the reactions attain equilibrium at a particular temperature. So here it will be H2 into RT, and then your pressure of I2 can be written as the concentration of I2 into RT. Alright. So here what you have is this RT, RT and RT square gets cancelled up. RT into RT and RT square gets cancelled up. So here in this case what you have is HI square to upon H2 and I2 is nothing but your Kc. So for this particular case we got that our Kc is equal to Kp or Kp is equal to Kc. Let's take up another example and now you find it out for the case of ammonia. We are restricting ourselves to very simple reactions today. Take another case of a homogeneous equilibria where you talk about the and tell me the relationship between the Kp and Kc. Work out the relationship between Kp and Kc according to the simple thing that you've understood. Now you know your Kc is equal to NH3 whole square divide whole square to the upon into H2 whole to the power cube. This is your Kc. Now what will be your Kp? Keep substituting each one of them. Kp will be equal to pressure of ammonia square upon pressure of N2 into pressure of H2 whole cube. Now what is pressure of ammonia? That is concentration of ammonia square into RT square, because this is CRT whole square, and then you have pressure of N2 will be equal to concentration of N2 into RT, and H2 will be equal to concentration of H2 whole cube into RT whole cube, such that you now have your, I'm just working it out here, you have your Kp to be equal to, you have Kc terms now because you have all the concentration terms. Kp is equal to Kc into RT to the power 2 minus 1 plus 3. 2 minus 1 plus 3. So that will be equal to Kc into RT to the power minus 2. So you can have one of the options. Please remember that you get many numericals based on the relationship between Kc and Kp in the exam. All you have to do is just work it out quickly and calculate. Now the short form of it is that you can remember that your Kp and Kc for a general reaction AA plus Bb giving Cc plus Dd can be written as, you have if we add an inert gas, no, then in that case it will just not change the pressure. So if the pressure is not changing, then it will not alter the equilibrium reaction. And moreover, we will be doing one of the laws that is known as the Le-Chatelier's principle, in which we will discuss the effect of causing any changes in any of the variables, what effect does it have on the equilibrium. So we will come to that. So the general formula for AA plus BB giving CC plus DD is, when you relate your Kc to Kp, it will be Kc will be, your Kp will be equal to Kc into RT to the power C plus D minus A plus B. These are the respective stoichiometric coefficients of your products and the reactants of the products and the reactions. So therefore Kp can be generally written as Kc into RT to the power delta N, where your delta N is the change in the number of the gaseous moles. Change in the number of the gaseous moles मतलब जितने gaseous number of products हैं, the number of moles of the products that you have in the gaseous form minus the number of moles of the reactants that you have. I'm just checking if you can do some question based on it. Okay, work out a question. The value of Kc, work out a question. The value of Kc is given to be as 4.24 at 800 Kelvin for the reaction CO gas plus H2O gas is giving CO2 gas plus H2 gas. Alright. the value of Kc is given. You have to calculate the equilibrium concentrations of CO, H2, CO2 and H2 given that at 800 Kelvin, that is also given. You have to calculate the equilibrium constants at 800 Kelvin given that the initial concentrations was like 0.1 molar and 0.1 molar of each. 0.1 molar, and please listen to this question. This is like picked up, all the questions that I am taking up today are picked up from your book only. The only thing is that if you understand the basic methodology of one, you can tackle all the others because they are not that difficult at all. Remember that if I say at equilibrium, let x moles of CO2 and x moles of H2 be formed. ये तो इनिशियल है. इनिशियल मतलब हमने स्टार्ट 0.1 मोलर CO से किया था, 0.1 मोलर H2O से किया था. So what were the concentrations of my CO2 and H2? They must be 0 and 0. At equilibrium, they are saying that at 800 Kelvin, your equilibrium is attained. So if you believe that x and x of this was formed, so what will be the concentration of CO and H2O will be left? It will be reduced by x and x amount. So it will be 0.1 minus x and this will be 0.1 minus x. ये चीज समझ में आई? So now it is like one step ahead. If you are given the concentrations, nothing at all. You just have to write down the expression for Kc. Now all of you all know how to write down the expression of Kc correctly. Once you write down the expression of Kc correctly, all you have to do is substitute the values of the concentrations and get the answer. Now if you are given the value of Kc, remember that the value of Kc means that you will be involving the concentrations of these only at equilibrium and at no other point. So here now your Kc will be equal to CO2 into H2 upon concentration of H2O into concentration of CO. That will be equal to x into x upon 0.1 minus x into 0.1 minus x. That will be 0.1 minus x whole square, and that will be equal to your 4.24 which is given in the question. ठीक है? This is equal to 4.24. Now all you have to do is just form a quadratic equation in terms of x and you will solve it. Just do it quickly. What you have here, I repeat it again, is you are given the value of Kc and you have to calculate the equilibrium concentrations. If you are given the initial concentrations, wonderful. Consider that x moles are formed. Consider that x moles are formed at the equilibrium, and if x moles are formed at the equilibrium, then you should understand that the leftover of the reactants will be the concentrations of the reactants at equilibrium, which will be 0.1 minus x and 0.1 minus x. Okay? This comes from the mole concept, that when 1 mole of CO reacts with 1 mole of water, it will always give you have to write down the balanced equation first. So you have to then talk about in terms of molarity. If you say that 1 mole of CO reacts with 1 mole of H2O, then it will give you 1 mole of CO2 and give you 1 mole of H2. So if you say x moles and x moles of this are formed, so it will be the same of this only. Or say if you would have had only one reactant also, like in case of PCl5, alright, PCl5 was 1. If I talk about this case of PCl5, let the initial concentration be C. ठीक है, अगर initial concentration C है तो ये कितनी है 0 और 0, क्योंकि initially तो starting products में 0 होंगे. Then you have this PCl5 is now getting dissociated to form PCl3 and Cl2. In this case, you say that 1 mole of PCl5 will always give 1 mole of PCl3 and 1 mole of Cl2. So if you say that x, after x extent of the reaction, either you call x as the extent of the reaction, or you say extent of the reaction means now it has moved to a direction where x moles of the products are formed. So x moles of the products are formed means that if x is formed of this, then the same amount, same number of moles will be formed of the other product. So X moles of the other product will also be formed. And what can get reduced from this? Only C minus X. Because इसमें से whatever moles is going to be reduced from here, the same number of moles will be produced for each of the reactants. And this you understand only after writing the balanced equation. So it is very important that first of all you all should be able to write down the balanced equation. Once you write down the balanced equation, only then you will be able to tackle these problems well. Two, say if you are having, okay, if you are having AB giving say 2P plus D, 2C plus D, why should we talk of A and B only? कुछ नया बन रहा है, ठीक है? So then in that case, now you would say that if initial concentration is C, what will be that of this and this? 0, 0, क्योंकि initial तो यही रहेगी. Now understand the equation according to the mole concept. 1 mole of AB is giving you 2 moles of C and 1 mole of D. So इसका मतलब अगर इसमें से मैं X moles reduce कर लूँगी तो I will get 2X moles of C and X mole of D. Got it? So be very clear about it. Because whatever number of moles are being used here, if 1 mole of this is being used, then 2 moles of C are formed and 1 mole of D is formed. So if X moles are being used up, then 2X moles of C will be formed and then X moles of D will be formed. This goes in accordance with the balanced chemical equation. So you should be balancing your equation in the first place very properly. Okay, for the previous question, coming back to the same problem again. I hope now you've understood, because this is an important part. If you're able to do this well, then you just have to put the values and do the simple mathematical calculations. So here, what you will have is, you will have say x square is equal to 4.24 into, you know what is a minus b whole square? A square plus b square minus 2ab. So you just have to open it up, that will be 0.01 plus x square minus 0.2x. That you can check it for yourself, minus this thing, and remember you will then get a quadratic equation, that is minus 3.24 x square minus 0.848 x plus 0.0424 is equal to 0 is what is coming out to be. Instead of quadratic equation, we can take square root of Kc also. Just if yes, you can do. That is a very simple and a shortcut method. This is like the normal subjective way of working. So in this case, you can actually, now there are two ways. I was just about to come to the next way also. Here in this case, what you have is, you can easily calculate x. How do you do it for a quadratic equation? I am just reminding you, plus minus of under root of b square minus 4ac upon. This is now one way. Now in order to have a shortcut method, what we can do is, here you have Kc is equal to x square upon 0.1 minus x whole square. Alright. Now in this case you should be able to find out how to find out the square root, because you take the square root of the entire expression. What will happen? Till this expression everything was clear. What will happen? You will take square root of Kc will now be equal to x upon 0.1 minus x. Looks simple. The only thing you should be able to find out the square root of 4.24, and I hope you remember how to do that. You do remember that 4.24, and then you take pairs after that, and then if you do that, you can easily get, because then your work is solved. So if you are good in finding out the square root, this method is good. If you're good in your mathematical calculations, this method is good. So I mean square root or this, but this reduces your work to a great extent, because in this case you get two values for x. In this case you get two values of x, and what will be those two values of x? Say if one turns out to be equal to 0.6 and the other turns out to be equal to 0.19 something, that is what the case will be in this case. So in this case, this value will be neglected. Why? Because the initial concentration was 0.1. So at equilibrium, you cannot have the reactant concentration to be greater than the initial concentration. So 0.19 will be greater. So in that case it becomes lengthier to decide which one is to be omitted out. So we generally prefer this method for a faster route. Okay. Done? Now I repeat, in this question you just have to know how to write down the Kc in the form of the concentrations of the reactants and the products at equilibrium in terms of X or alpha or something else which defines the extent of the reaction. Then we can now talk about some kind of a heterogeneous equilibria also, and I told you that what are heterogeneous equilibria? Heterogeneous equilibria is the case where you say that your one, what is this? This is the case of a heterogeneous equilibria where you know that one of the phases will not be the same, in which one of the reactants or the products may have a maybe in a different phase. Say you have another example, CaOH twice, CaOH twice plus say water in the aqueous form. You take it in the aqueous form, say this is solid, this is, you make it in the aqueous form. So what does it mean? It forms the ions in the aqueous solution plus 2OH minus. One thing that I'd like to point out here is generally your ions exists in solution in a very stable form. So whenever you have a solid and you put it in the aqueous form, what you get is you get the ions in this particular form. So this is like another case of a heterogeneous equilibria, because here what we have is, one of the reactants to be in a different state in comparison to that of the products. Okay. So then next, let me just ask you to write down the equilibrium constant for this reaction. Solid plus CO2 gas. Alright. In this case, you will generally write down the Kc as, what will you write down the Kc as? You will be writing it as concentration of CaO into CO2 upon CaCO3. But remember that the concentrations of the solids at equilibrium will remain a constant, because the solid will remain a solid. It will only be the gaseous form which will keep coming onto the surface and keep going back. Alright. So that will be what will make the equilibrium attain a dynamic state. So there is a question from the previous numerical that we had just done. So if we will take the square root, so one of the x values will be omitted. Yes, and I told you the reason for that also. Why was it omitted? Because it was giving you a weird value of the concentration of the it was giving you a weird value of the concentration, which was actually telling you that it is more than the concentration, initial concentration of the reactants, which is not the case. Okay, so then we have Kc. Now I am telling you, your Kc can be written as CO2 into CaO upon CaCO3, where you know that CaO will be in the solid form and CaCO3 also in the solid form, which will remain a constant. So we can write down the modified form of Kc in this case, which will depend only on the concentration of the gaseous molecule if this and this are existing in their pure solid state form. If it provided they are existent in their pure solid state form. Okay. And then in that case, what will be, how will be Kp related to it? How will be Kp related to Kc? Kp will be equal to Kc, because this will be equal to PCO2, so that will be equal to Kc into RT. Yeah. So that will be Kc into RT. Alright. So remember that in these cases you will be taking it. Okay, now write down the Kc for this reaction then. Write down the modified Kc for a heterogeneous equilibria. So remember that whenever we talk about the heterogeneous equilibria, we will consider the solid state, or if it is a liquid state existing in its pure form, then you will take its concentration to be equal to unity. Or You cannot take it to be equal to 0. You take it to be a unity or a constant, and then you write down the modified rate constant, and write down the modified rate constant if you have understood this for Ni solid plus 4CO gas giving NiCO4 gas. Alright, and write down the relationship between Kc and Kp also. You are supposed to write down, now do it directly, get Kp is equal to Kc into RT to the power delta N. So you can easily take where delta N is the change in the number of moles of the gaseous molecules, or say the number of moles where you have something in the dynamic state and not a constant in its pure state, or not a reactant or a product which exists in its pure state. Consider nickel in the solid form here to be in the pure state. So you can write down your Kc as, I am starting to work on it now, NiCO4 upon CO to the power 4. So therefore, here your Kp will then be equal to Kc into RT to the power, see Kp is equal to Kc into RT to the power, what will it be? 1 minus 4. 1 minus 4 will be minus 3. So you may be given the relationship as Kp is equal to Kc by RT cube. That's also the way in which it can be given. Remember that in heterogeneous equilibrium, pure solids or liquids, no, see, I am just coming to this point. There is a doubt on the board that ma'am, won't we consider liquid state in constant? That's what I'm saying, that whenever you talk about the heterogeneous equilibria, solids or liquids must be present for in equilibrium for them to exist, and then if their concentration or a part does not appear in the equilibrium constant, then that means they are existing in their pure liquid state only. Let me just give you another example to explain this further on, that if your liquid is existing in the pure form, then you ignore that as well. Say for example, generally what kind of a liquid can you be thinking of to be existing in the pure state? Some liquid that you know very well, water. So wherever you have H2O also in the liquid state, you know that it will be existing in the pure state. If you are writing H2O, means you are talking about simple water which is in the pure state only. So that will also be actually modified and taken to be as unity in your rate constant. I am saying that unity so that you understand that that has to be modified and taken as a constant value, so that you write down your modified Kc. If you have understood the doubt, that means for pure liquid or pure solid state, you will just be ignoring that concentration in the Kc term. So take down this, if you have understood this, write down the Kp Kc value again for this. So Ag2O plus 2HNO3. Ag2O is in the solid form, 2HNO3 is in the aqueous form. That's giving 2AgNO3. That's in the aqueous form, plus H2O, that's in the liquid form. Now write down. If you've understood this particular thing, that you can take down for a pure liquid or a pure solid case, then you can easily write down the Kc for this reaction as well. So you have Ag2O in the solid form and you have H2O in the liquid form here. Remember that it is really important that in the heterogeneous equilibria you have the pure solid or the pure liquid existing in the equilibrium form. So done. It shouldn't be taking so much time. Why you writing and writing? Here Kp will be equal to Kc. Kp is equal to Kc because your concentration terms are just to the same power, so your RT terms get cancelled, and you will have your Kc to be equal to AgNO3 whole square upon HNO3 whole square, right. So here you have your Kc to be equal to AgNO3 concentration whole square upon HNO3 concentration whole square, fine. So now let's talk about the applications now of equilibrium constants. Applications of equilibrium constant. First of all, Equilibrium constant is applicable only when it is applicable only for those concentration of the reactants and products which have attained equilibrium. This I have stated to you that you should have actually have the value of Kc only with the concentrations which are attained at equilibrium. You will not use any other concentration. Remember that your therefore Kc is independent of the initial concentrations of R. They are independent of the initial concentrations of R and concentration of the products. Whatever the initial concentration is, your Kc has got nothing to do with it. Then the third thing I told you is Kc is dependent on temperature. Kc is dependent on temperature. That each of the reactions will have a particular value of Kc at a particular temperature. The moment the temperature changes, the Kc value will also change, and different reactions at the same temperature will have different values of Kc, because now you know that the expression of Kc will be different for all. So how can you think of the Kc value to be the same? So remember that Kc is highly dependent on temperature. Remember that here the Kc for the reverse reaction, now some important things that we have done. What have we done for Kc? The Kc for the reverse reaction will be 1 upon Kc, and when you multiply it with some factor n, Kc to the power n. If you multiply it with 1 by n, it becomes Kc to the power of 1 by n. And then last but not least, we have done the relationship of Kp and Kc. What is that? Kp, please do not get confused. That is why I did the derivation first. Kp is equal to Kc into RT to the power delta n. So Kc comes on the right. This is one thing. Then another important thing is to understand the range of Kc. Say if the value of Kc is much greater than, now you understand Kc. The moment I say Kc, you know products in the numerator, reactants in the denominator. Ab to chap gaya. Okay. So now if I talk about Kc value to be much greater than a particular value, say 10 to the power minus 10 to the power 3. ठीक है, इस चीज को just understand कर लो that if you have your Kc value to be much greater than or simply greater than say a great value of 10 to the power 3, what will it mean? That the product concentration is very high, right? This means that the product concentration is very high and your reaction has approached completion, right? And completion means that your equilibrium state has not actually properly been attained. Or you say that when your Kc is less than 10 to the power minus 3, then in that case you say that the reaction will highly proceed, the reaction is rarely proceed. So when I talk about Kc to be less than 10 to the power minus 3, then in that case what will it mean? That now the concentration, if this value is very low, because you know that your Kc is directly proportional to the concentration of products and it is inversely proportional to the concentration of the reactants. तो इसका मतलब अगर Kc value is very low, then the reactant concentration is very high. And if your reactant concentration is very high, then that means the products are negligibly formed. The products are negligibly formed, which means that the reaction is rarely proceeding in the forward direction. And so that is why for the equilibrium, the best range is considered to be in between 10 to the power minus 3 when your Kc is in between 10 to the power minus 3 and 10 to the power plus 3. This is the best range where you can have the rate of the forward reaction to be equal to the rate of the backward reaction with comparable ranges or the concentrations of your reactants as well as the products. Okay, so next after that we move on to check out more applications of Kc, how it can be utilized to predict whether a given reaction can occur or not. Kc can also be utilized to find out whether a given reaction, now Kc is a constant, this you understand, Kc is just a constant, You all understand this, and this is that constant which can only be related to that state which is at equilibrium. But say if the reaction has just started to set down in equilibrium, sometimes in many of the books you find it written as this also. If your AA plus BB, this, alright, like CC plus DD, this would mean that the reaction has just started and now it has started to form your C and D. So products are starting to get formed, alright, and because C and D, जैसे C and D will start getting formed, they will try to move back in the backward direction also to form your A and B again. ठीक है? So at equilibrium both of them are equal. So at any stage of the equilibrium, generally shown like this, at any stage means abhi the perfect equilibrium has not been set. If I am given the concentration of the reactants and the products, I can write down the reaction constant for that according to the law of mass action. Say I call that reaction constant Q, because my concentrations that are provided for A, B, C and D are not at equilibrium. इस चीज को ध्यान से समझना, because there is a confusion between Kc and Qc or Kc and Q, because Kc is the that ratio in which the concentrations are at equilibrium, where exactly your rate of forward reaction is equal to the rate of backward reaction. But when you are talking about the reaction constant, then you are talking about the concentration at any stage, at any stage. So here in this case, again according to the law of mass action, I can write down my Q in terms of concentration, so you call it QC or Q, as C to the power C, D to the power D. This you can easily understand. बट अब डिफरेंस क्या है इसमें कि ये कॉन्सेंट्रेशंस किसी भी स्टेट की हो सकती हैं, ठीक है? तो अब इस केस में we'll see three cases. One, when your Q is much greater than Kc. Second, when your QC is less than Kc. And third, when QC is equal to Kc. Now see, when your QC is greater than Kc, that means the QC means QC is directly proportional to the product concentrations, वही same चीज है. तो इसका मतलब the products which have been formed now are greater than the equilibrium concentration of the products. So that means the reaction is moving in the forward direction. If that is the case, then I will have the reaction, अगर ये ज़्यादा बन गए हैं तो reaction किस direction में move करेगी? Backward. बात समझ में आ रही है? I repeat it again. If QC is greater than Kc, इसका मतलब मेरा equilibrium से आगे जा चुका है reaction. Products have been formed in extra amount. So then in that case, this will imply that now my reaction direction will be reverse. That means my reaction will move from right to left. I will explain this again. First, confuse yourself completely. What is this reverse reaction? Reverse reaction is like because of this. Let's come to the next case and maybe it becomes better. QC, any concentration. तो इसका मतलब अभी the concentrations which are there are for the products is less than the concentrations at equilibrium. क्योंकि इसके अंदर जितनी भी concentrations है वो सारी equilibrium वाली हैं. इसके अंदर कोई state वाली हैं और उससे we are deciding whether we have to go in the forward direction or we have to come back in the backward direction. Up if the concentration of the product is less, that means reactants is more, इसका मतलब अभी the reaction can move towards equilibrium, towards more formation of products. So then in that case my reaction will be a forward reaction. That means it will move from, I was writing light to right. It will move from left to right. Acha, and when QC is equal to Kc is something that you all will understand the most easily. That means the concentration are now just the same. So they are at equilibrium. So in this case there will be no change in the reaction and you will have the reaction is in equilibrium. You say that when QC is in equilibrium, so this means that there will be no further reaction. Now a question. Kc is a type of QC? Yes, Kc is a type of QC only at equilibrium. Alright, but QC is QC because QC is concentration at any point in time. It is the general ratio. I am giving you the concentrations that abhi I have 0.1 of this, 0.1 of this, and I am saying 0.5 of this and 0.5 of this. This is just any time. So I am not talking about the equilibrium. Then what you can find out is, can you find out Kc here? No. What you can find out is QC. And QC can keep varying from time to time. QC आपका change होता रहेगा. That is called the reaction constant at a particular stage of time. लेकिन Kc will remain constant for a particular reaction at a particular temperature. ठीक है? Now, just repeating this once again. अभी तक we were just referring to the equilibrium constant. That equilibrium constant was defined according to the law of chemical equilibrium, or another name for that is law of mass action, where you say that it is C to the power C, D to the power D upon A to the power A into B to the power B, where that is small a, small b, small c and small d, which means that they are the respective stoichiometric coefficients, and within the bracket terms you have the concentrations of each of the products and the reactants. So here what we get is, when I say at equilibrium it would have been Kc, but if I say at any state, then it is QC, alright, or Q, which is written in your book as Q only. So it is given as QC. Q. So now this QC is at any state. We can relate this to Kc. How? Once you find out whatever state concentrations are given to you, you find out your QC. Okay. Once you found your QC, check whether that is greater than Kc or less than Kc. उससे आपको पता चलेगा whether the reaction has to go in the forward direction or in the backward direction. If QC is greater than Kc, इसका मतलब my concentrations of the products have already become high. So इसका मतलब in order to get back to equilibrium, I'll have to come back. So the reaction then will follow a reverse reaction, and it will move, the direction will be from right to left. But if QC is less than Kc, then that means my reactants are more and products are less. If QC is less than Kc, QC less means my products are now less and reactants are more. QC का relation, ठीक है? तो अगर QC मेरा कम है, इसका मतलब मेरे reactants ज़्यादा हैं, और अगर मेरे reactants equilibrium वाले से ज़्यादा हैं, then in that case I have to move in the forward direction. So then I will have the direction from left to right. And then if QC is equal to Kc, then the reaction is said to be in equilibrium, because agar sari concentrations are the same as the concentrations at equilibrium, then there will be no reaction. If you've understood this, take down a simple problem, and we'll take up complicated problems in the next class only. Take down a simple problem. Kc for the reaction is given as 57. ठीक है? Kc for a particular reaction is given as 57. And you have to predict the direction of the reaction now. For the case of HI, I am not writing the HI reaction again. That is, HI is 0.4 molar. You have H2 to be 0.1 molar, and you have I2 to also be equal to 0.2 molar. Alright, now you have to find out whether the reaction will move in the forward direction or the backward direction. These are the concentrations given at a particular state. अब आपको बताना है यहाँ से ये इक्विलिब्रियम की तरफ फॉरवर्ड जाएगी या बैकवर्ड. सो इन दिस केस your QC will be equal to, this is for the formation of HI, this is for the formation of HI. So write down the reaction. Your QC will be equal to then HI square upon, अब reaction तो आपने ये बहुत बार लिख ही लिया आज, so that will be equal to 0.4 का whole square upon 0.1, and you will have 0.1 into 0.2, that will turn out to be equal to 8.0. So you see that your Kc is equal to 57. So QC will be much less than KC now. तो forward. So guess मत करना because there will be only three options: forward, backward, at equilibrium, or none of these. So in this case you will have QC to be much less than KC, and that will result in a forward reaction. Take down another problem. Consider the reaction 2A giving B plus C. Consider the reaction Alright, consider a reaction where you have 2A is giving B plus C. The Kc for this reaction is given to be equal to 2 into 10 to the power minus 3, 2 into 10 to the power minus 3, and what you have is the composition of the mixture is A is equal to B is equal to C is equal to 3 into 10 to the power minus 4 molar. In which direction the reaction will proceed? The data that is provided is this. You just have to tell in which direction the reaction will proceed. So remember, in all of these cases you are calculating now your Q. In all these reactions you are calculating your Q. Q in this case will be equal to, first of all write down, remember that you should be carrying it in your mind that it is B into C upon A square, and then just substitute the values directly. Do not go on to write down the expressions for the entrance examinations, just write straight away the values. So it will be B into C upon A square, and what is that value turning out to be? In this case it's very simple. So Q is equal to 1, 1 is much greater than 2 into 10 to the power minus 3, that's your Kc. So what does that mean? In this case it will be, when Q is greater than Kc, it will be the reverse or the backward direction. That means your reaction will proceed back. The reaction will proceed back. So just do this summary in just about half a minute's time. Compare your Q and C and then predict whether. Let me just take up some more questions from the previous things also so that nothing is left out. Say if you have 2NOCl is giving 2NO, another question, plus Cl2. Alright, take up another question. This question is simple. Now you know if Q is less than K, then in that case the reaction will be forward. If Q is greater than K, the reaction is backward. So Q less, एक याद कर लो, Q less than K, that means it is forward. जहाँ K ज़्यादा है वहाँ पे forward reaction है बस. ठीक है? Now for the next question, I have written the reaction on the board. Kc is given as 3.75 into 10 to the power minus 6 at 1069 Kelvin. Calculate Kp. Calculate Kp for this reaction. I am giving you the next question. This was one question where you were comparing the results. This is another question. Alright, quickly do it. I am giving you again, I'm telling you the question again. You are given a reaction. 2NOCl is giving you 2NO plus Cl2. You are given the value of Kc and temperature also. You have to tell me the value of Kp. All are in gaseous state. Yes, that's a good question. I should have given that. So in this case, you will have, tell me the relationship first. It will be Kp will be equal to Kc into RT to the power
3 minus 2.
that will be equal to 2 plus 1 minus 2. So that will be equal to 3 minus 2 and that will be equal to 1. So then you just have to substitute the values. That will be equal to 3.75 into 10 to the power minus 6 into
8.0.
Why do you take this? Because if you have to express the pressure in bars, then you will be using liter atmosphere or liter bar per Kelvin per mole. You remember the values of R. I had given you the values of R to mug up so that you remember them for the numericals. It is 8.314 joules per Kelvin per mole and it is 0.083 or 0.0821 something. That can be taken accordingly. So that will be 0.083 into 10 into temperature is 1069. So you just have to calculate this to calculate your Kp. Now, if given that the concentrations of NOCl, NO and Cl2 at a given point in time are 10 to the power minus 2, if the concentration of NOCl, NO and Cl2 is 10 to the power minus 2, predict the direction of the reaction. इससे ज़्यादा simple नहीं होगा, करके देखो. Just quickly do it. I am telling you that you are given the concentrations at a particular point in time of NOCl, NO and Cl2, that is 10 to the power minus 2. You have to write down now the expression of Q completely. Q will be equal to NO square into Cl2 upon NOCl square. So that will be equal to 10 to the power minus 2 means 10 to the power minus 2 whole square 10 to the power minus 4 into 10 to the power minus 2 upon 10 to the power
minus 4.
10 to the power 4.
Minus 4.
Oh sorry, 10 to the power minus 2 whole here, 10 to the power minus 4. So this gets cancelled. You have Q to be equal to 10 to the power minus 2. Now in this case, Q is greater than K, and if Q is greater than K, then it is backward direction. क्योंकि जहाँ पे K ज़्यादा है वहीं forward बस. So K less means backward direction. So you see that if you remember just these simple relationships, you can tackle numericals very easily. Take up one more question now. Say value of Kp is given as 3 now. The value of Kp is given as 3 at 1000 Kelvin. The value of Kp is given as 3 at 1000 Kelvin for what reaction? I am writing it on the board. For carbon dioxide plus carbon. Carbon dioxide is in gaseous state. You have carbon in the solid state giving 2CO gas. I have told you that the Kp value that is given is equal to 3.0 at 1000 Kelvin for this reaction. Now if pressure of CO2 is equal to 0.48 bars and the pressure of CO is equal to 0 bar initially and pure graphite is present, calculate the equilibrium pressures. Calculate the equilibrium pressure of CO and CO2. Calculate the equilibrium pressures of CO and CO2. Remember again, now you will have to use the same funda that I explained. You will have to use the mole concept again here because you are given the initial pressures, you have to calculate the equilibrium pressure. Kp value is given to you. Alright, so in this case, what you have is for the solution, you write down the reaction again, that will be CO2 plus C is giving you 2CO into gas. This is your solid and graphite is present in the pure form, means that this will not be considered in the expression. So here you have the initial pressure as 0.48 and this is 0. Now you tell me if X moles are of this are reduced, if X is the extent of the reaction, that means 0.48 minus X, और जितने मोल्स यहाँ reduce हुए हैं उसका double.
2x.
So 2x will be formed. Alright, and then write down the expression of Kp. Now you know Kp will now be equal to pressure of CO whole square upon pressure of carbon dioxide. You have the values, just substitute the values at equilibrium. Kp is equal to 3 and pressure of CO is now equal to 2x whole square upon, you will have 0.48 minus x. 2x whole square minus upon 0.48 minus x. Now here it will not be advisable to take the square root, so you will have to form the quadratic equation quickly in this case, and you can just completely solve it. So in this case you will get that the quadratic that you will form is, quickly form it, that will be something of the type of 4x square. It will be, the quadratic will be 4x square plus 3x minus 1.44. I am sure you all have arrived to the state, and then you know x is equal to minus b plus minus of under root of b square minus 4ac upon 2a. So you can easily solve that to get the value of x as 0.33, and then the pressure of CO will be equal to 2 into x. You can easily do that. Pressure of CO will be equal to 2 into x. That will be equal to 2 into x, that will be equal to 0.66 bars, and then you will have pressure of carbon dioxide can also be easily found, that will be 0.48 minus x, that is equal to 0.15 bar. Okay, I hope this question is absolutely clear, because if you are able to understand this particular thing, then you can solve questions of this type. And also remember that given that your solid or liquid is in the pure state, you can always omit it out in the final expression. So now here what we have is, this is like done, and another thing, now I extend this question. Calculate Kc value. Calculate the Kc value at, temperature is not given to you, right? At 1000 Kelvin, yeah, the temperature is also given to you. So calculate the Kc value. In this case, remember that RTs will not cancel off. So what will you have? Your Kp will be equal to Kc into RT to the power delta N. What will be your delta N in this case? Kp is given as 3. So you will have your 3, RT is, delta N is 2 minus, why 2? 2 minus 1. The solid is in the pure state. So you consider that to not to be, I mean that's just a constant. So in that case you will consider the change in the number of the gaseous moles only. And remember what equation have you used here for this conversion? RT, how did it come? PV is equal to nRT. What is that? Ideal gas law. So gas law. So if you are considering gases, it will be, the number of moles will be 1. So delta N will not be 0, please take care of that. Here in this case delta N will be equal to 1. So I just gave this question like that. Good that I gave it. Done? Now next is like, what have we done till now is like hardly anything. We've just understood Kc, how Kc changes with the reactions, and how Kp is related to Kc, and how Q is related to Kc. That is the only thing that we've done, and we've understood as to how the reaction will move in the forward or the backward directions dependent upon that. So now let us see how do we actually can calculate the equilibrium concentrations also. This is also another thing, something that you all should know. First of all of you should be writing down the balanced equation. In order to solve any question, in order to calculate the equilibrium concentrations, first of all you all should be writing down the balanced equation. Then make a list of initial concentrations that you all do. You all do a list of make a list of initial concentrations, that is what is the change in the concentrations in going from one state to another, and also the equilibrium concentrations are generally written underneath. Then what we use is we use the stoichiometry to determine that concentration. This is the question that you've already asked me. You use the stoichiometry to determine the concentrations, this, and we've taken up questions already on it, and then we substitute to get the value of x. Then we generally substitute to solve for x. This is what we have done. And results can generally be checked by back substitution also, because I have told you again that if I give you anything which is like goes in like 2ab is giving you 3c plus 4d. So now let me just check if this is the balanced chemical equation. The very first step is, I'm just repeating this again for everyone because you will have many questions based on it. If this is the balanced equation that I am giving you, then in that case what will be, they say the initial concentration is like C, and this is say 0 and 0. Now if I say that equilibrium is attained after x extent of the reaction or alpha extent of the reaction, then in that case if I say that x moles are getting formed, then 3x of this will be formed and 4x of this, and what is getting reduced from it is is C minus, why 2x? Yeah, because here you have 2 moles, sorry. So that will be C minus 2x. So in this case you have to take care that each number of stoichiometry coefficient is taken into account accordingly, because here 2 moles are giving rise to 3 moles of C and 4 moles of D. So only when 2 moles of A are reduced, then you will have 3 moles of C and 2 moles of D getting formed. So this is like an important thing that needs to be remembered. And using this phenomena you can also actually do up for weak electrolytes, like we have a weak electrolyte CH3COOH. You know it will be weakly dissociated to give you CH3COO minus plus H plus. Now if say C is the initial concentration and say 0 and 0, here I am not talking about the number of moles which are formed, but rather I am talking about the extent of the reaction to be say alpha. This is like कि कितने extent तक my reaction has proceeded. I am just relating it because this reaction is again in equilibrium. So if x is alpha is the extent of the reaction after say some time t, then if C minus C alpha is reduced here, then what will be formed here? It will be C alpha and C alpha. Alright? That will be C alpha into C alpha, and using this I can easily calculate my equilibrium constant. What will be my equilibrium constant Kc here? That will be C square alpha square upon C into 1 minus alpha. C and C will get cancelled off. So I will have this as C alpha square upon 1 minus alpha. Now if I am saying that this reaction proceeds to a very little extent, तो इसका मतलब alpha is going to be much less than 1. Because if this reaction proceeds to a very little extent, then this clearly means that alpha will be, yes, there also it is like,
But in that case, we had chosen C minus X.
in that case we are not considering the concentration, but I stated that if X moles are getting formed. So in this case what is getting formed? C alpha moles and C alpha moles. Alright, and if I say if this is the concentration which is getting formed, then what is getting reduced from here? C minus X. So all these things are interrelated only. Right, so here if I multiply, had I taken only alpha and alpha here, then I would have done only C minus alpha. Just as you just corrected me when I was writing C minus X and you told me it has to be C minus 2X. That goes in according to the stoichiometry of the balanced equation. So here, till here it was clear? We have already understood how to balance our reactions and how to write down the concentrations at equilibrium. Say if C is the initial concentration, then the initial concentrations of this will be 0 and 0, and then if say alpha is the extent of the reaction, then we say that if alpha is the extent of the reaction, what will be the concentration of the products by that time? It will be C alpha into C alpha, because alpha is the extent of the reaction. And if C alpha of this has been formed, what will get reduced from here? C alpha. So it will be C minus alpha. Now we know how to write down. I am repeating it again. If
C alpha instead of just alpha.
yes, why you wrote C alpha instead of just alpha? Here I am just relating it to the concentration term. Say if X is the extent of the reaction, I am saying that the reaction is proceeded by a particular extent, then I am saying that the concentration increase will be according to that. ठीक है? तो अगर मेरी X alpha एक्सटेंट तक बढ़ गई है रिएक्शन, तो मेरी इसकी कॉन्सेंट्रेशन उतनी ही बढ़ जाएगी, उतने नंबर ऑफ टाइम्स बढ़ जाएगी. सो दैट विल बी सी अल्फा इनटू सी अल्फा. ओके, गेट द पॉइंट. इनिशियली तो ये 0 0 था. अब आई एम सेइंग कि अल्फा टाइम्स मेरी रिएक्शन हैज इंक्रीज्ड, and whatever has to get reduced from my reactants will be produced in my products accordingly. So here I have, if I have C alpha number of moles and C alpha number of moles of products getting formed, so I know it's directly related to my acetic acid as minus C alpha will be there, because 1 mole of acetic acid is giving me 1 mole of acetate ions and 1 mole of H plus. ठीक है, तो इस केस में we have Kc to be equal to C alpha square upon 1 minus alpha. This is what we got because that Cc term got cancelled off. So I'm just writing this Kc term again, that will be C alpha square upon 1 minus alpha. Now if my electrolyte is a weak one, then my alpha will be much less than 1, क्योंकि अगर वो वैसे ही weak है, डिसोसिएट होगा ही नहीं. ये इक्विलिब्रियम वो फर्स्ट केस वाला है जिसमें you have the undissociated form much more than the dissociated forms. So then in that case my extent of the reaction as it is will be very low. अगर वो बहुत low है तो 1 से तो बहुत कम होगा, और अगर 1 से बहुत कम है I can just ignore it in the denominator. ठीक है, so उस केस में मेरा Kc will be equal to C alpha square. So I can find out a relationship for alpha that will be equal to under root of Kc by, ठीक है. So for weak electrolytes your extent of the reaction can always be found using this, and this entire thing we'll be doing it again in ionic equilibria quickly now next time, and this law is known as the Ostwald's dilution law. So alpha will be equal to under root of Kc by C, where alpha is the extent of the reaction, C is the concentration of the reactants that we taken up initially, and K is your equilibrium constant. That is your equilibrium constant. Let's take up one more problem. See, consider the question is 13.8 grams of N2O4. 13.8 grams of N2O4 was placed in 1 liter reaction vessel. Were placed in 1 liter reaction vessel. Were placed in 1 liter reaction vessel at 400 Kelvin. At 400 Kelvin and allowed to attain equilibrium, and it was allowed to attain equilibrium. So it generally gives 2NO2 gas. Alright, the total pressure was found to be total pressure. Now the total pressure would mean the pressure of N2O4 plus the pressure of NO2. So the total pressure was found to be 9.15 bar. You have to find out what is Kc at equilibrium, what is Kp. Kc anyways will be at equilibrium only, Kc and Kp, and find out the partial pressures, at equilibrium. Now do this reaction. Here in this case, first of all, I would suggest that you have don't remember the ideal gas law equation, which is equal to PV is equal to nRT. If you know that, you can easily calculate the initial concentration also, or you can calculate you are given the total this thing, work it out. I repeat the question. The question says that you have 13.8 grams of N2O4. Okay? N2O4 are already there in 1 liter reaction vessel. After some time that attains equilibrium. And when it attains equilibrium, you know that the total pressure that is given to be is 9.15 bars. Okay? Now you have to calculate Kc, Kp and the partial pressure at equilibrium. Molecular mass of N2O4, I will tell you, that is 92. You can easily calculate it also. Molecular mass of N2O4 is 92 grams. So you can calculate your N. What is your N? N will be equal to given mass
13.8
upon 92, that will be equal to 0.15. Okay. R will be taken to be in 0.083 or 0.0821, whatever you want, liter bar per mole per Kelvin. Temperature is given to you as 400 Kelvin. So you can easily find out the pressure. You can easily find out the pressure from here. What will be the pressure? It will be 0.15, volume in number of moles is 0.15 into 0.083 into 0.083 into 400 divided by 1 only. So the pressure will turn out to be equal to 4.98 bars. The pressure will turn out to be equal to 4.98 bar. Then you have your N2O4 is in equilibrium with your NO2, right? So now if you have 4.98 as the initial pressure, what will be the initial pressure here because of NO2?
0.
It will be 0, because this is the initial concentration of NO2, that N2O4 that was given to you. Initial mass of N2O4 that was given to you. So now when you are given the given mass, you know the molar mass can be calculated. Nitrogen is 14, oxygen is 16, 16 4 is 64 plus 28, you get 92, and then you find out the number of moles is 0.15. R is already given to you, you know that value. Temperature is 400 Kelvin. Pressure will be equal to N by V into RT. Volume is equal to 1 liter. You substitute the values and get the pressure. Clear till here? Now you have to follow the normal methodology that you know. Once you've calculated the initial pressure, you know 4.98 is now the initial pressure. This will be 0, and then you get it as 4.98 minus x, and what will this be then? If this is 4.98 minus x, this will be 2x. Alright, so you can easily write down the expression for Kp then. You can write down the expression for Kp, and that now you know that P total at equilibrium is equal to P of N2O4 plus P of NO2. What is your total pressure? That is equal to 9.15. This is again that is given to you. The total pressure at equilibrium is given to be as 9.15. What is your this? What is Pn2O4? That is 4.98 minus x. What is your pressure of NO2? That is equal to 2x. You can easily find out x from here. Your x is turning out to be equal to 4.17 bar. Once you found your x, you can easily now calculate your Kp. What will be your Kp? It will be the pressure of NO2 whole square upon pressure of N2O4. And what will be your pressure of NO2 whole square? That will be 2x whole square
4.1782 का whole square
upon
4.98
minus x.
4.1.
So you calculate that, and then once you know your Kp, you can easily calculate your Kc. Your Kp is equal to Kc into RT to the power of minus 1 in this case, 2 minus 1. So you can easily find that out. Okay. I repeat this question once again. It's a simple question picked up from your book where you are given. So remember that all these questions will be the ones which will be modified. So next time we'll take up complicated problems because chemical equilibrium has little formulae, but you have a lot of numericals to practice in this different twisted forms. For that you have to remember only the basics that we'll revise once before I complete it up. What was given in the present question was you were given the initial mass of N2O4. Using that mass, what did we do? We calculated our initial pressure. ठीक है, initial pressure हमने कैसे निकाला? Using PV is equal to nRT. That goes without a saying that you must have understood all this. So हमने find out करा pressure as 4.98 bars. Because that was simple substitution, number of moles could be calculated using the given mass. R value was known, T value was known, V value was known. So the pressure, initial pressure was calculated for N2O4 as 4.98. Once that was calculated, I know how to write down my reaction. That initial pressure, if it is for the reactant, for the product it will be 0. At equilibrium, if 2x is the pressure for my product, then my for the reactant it will be 4.98 minus x, that goes in according to the stoichiometry. Okay, so that becomes equal to 4.98 minus x, and this becomes 2x. Now at equilibrium, this total pressure is equal to 9.15, which is given in the question. Using that, I calculated my x. Once that x is calculated, then our work is done because we can write our Kp and then we can relate our Kp and Kc also. So this is like one thing which is again done. Now another thing that I'd like you to do is we've done this. The only thing is you can take up just one last question before I move on to the another concept of Kc. You have 3 moles of PCl5. All right, just take this. Now you are given 3 moles of PCl5 kept in 1 liter closed vessel, which is allowed to attain equilibrium at 380 Kelvin. Just take down the keywords. 3 moles of PCl5 are allowed to attain equilibrium in 1 liter vessel at 300 Kelvin. Okay, at 380 Kelvin, sorry. Calculate the composition of the mixture at equilibrium. So you have to calculate the composition of the mixture at equilibrium. You are given the value of Kc now, which is 1.8 Kc now, which is 1.80. All right, which is 1.80. So now you have PCl5. What is the reaction? It's giving PCl3 plus Cl2. The initial molar concentration is given to you for PCl5. That's very simple. What is the initial molar concentration? That's like 3.0. You have here 0 and 0. So now at equilibrium, say if x moles of this are formed and x of this are formed, then you now know what will be your PCl5. That will be 3 minus x. And if that is the case, you can easily write down your Kc. Your Kc, which is given as 1.8, will be equal to x square upon 3 minus x. So you can easily get your x from here, solve the quadratic equation. X square plus 1.8x minus 5.4 will be equal to 0, and you can calculate your x from here. Once you get your x from here, you can calculate the equilibrium concentrations for all. Okay? Once you get your x from here, again according to minus b plus minus under root of b square minus 4ac, you will get the value of x as 1.59 molar, which is given, and then you have as the answer. PCl5 will be equal to 3 minus X, which will be equal to 3 minus 1.59, that is equal to 1.41 molar. So you are given the concentrations of, so that ways you can give the composition of the mixture at equilibrium, means that you are supposed to give the concentration of the reactants and the products at equilibrium, and this again goes according to the stoichiometric coefficients of the reaction that you should know. So remember that the balancing of the reaction is very important, because when you write down the concentrations at equilibrium, उसके अंदर वो stoichiometric coefficient डलेगा. So that has to be taken into account, and provided you are given the initial terms, and the initial terms will always be provided to you. अगर वो नहीं दे रखा तो जैसे previous question में we calculated PV is equal to nRT, similarly in some of the cases we can even calculate the concentration using the pressure. See, in the previous question, if the concentration was given to us, then using, if the pressure would have been given to us, we could have calculated the concentration also. So initial things if are known to you, then the rest of it should be very simple. Clear? Now write down another relationship which is very important. Now you remember that we have talked about the equilibrium reactions now, and we know that equilibrium will be the state where my QC will be equal to KC. और हमने इससे पहले कौन सा टॉपिक पढ़ा है? थर्मोडायनेमिक्स. The topic that we did before was thermodynamics. In that, I told you that the reaction will be spontaneous and will move in the forward direction when your delta G is less than 0. When your delta G is negative. I hope you remember that. What was the benefit of using that? Let me just help you recall. What was our delta G? Delta G was equal to delta H minus T delta S. Alright? इसका फ़ायदा ओवर डेल्टा एस क्या था? हमारा डेल्टा एस में ये था कि if my delta S is plus positive, then my reaction is spontaneous. If it is negative, then it is non-spontaneous, मतलब it will not occur. Now this delta S information was available only for the system. But what was deciding on to the process whether the reaction is possible or not is your total delta S. And what is your total delta S? That is your delta S system plus delta S surroundings. So this only gives you an idea whether the reaction may or may not be feasible, right? But what decides, and unless and until you have the total delta S with you, delta S surrounding मतलब क्या है? System was only the system that we were considering, surrounding was all the rest of the universe. So delta S surroundings was quite difficult to calculate. So delta S system was like some data which is insufficient. So we prefer for spontaneity which factor? Delta G factor. और delta G का benefit क्या है? कि it talks about, in this case even if we have the data related to the system, we can calculate our delta G. And delta G, if it is negative, if delta G is negative, then the reaction is spontaneous. If delta G is positive, then the reaction is non-spontaneous. And now I am telling you one more added thing, that if delta G is equal to 0, then the reaction is at equilibrium. If delta G is equal to 0, then the reaction is in equilibrium. Okay? And another thing that we had done before in thermodynamics is delta G is equal to minus T delta S total. ये मैंने बताया था, याद है? You can actually get a relationship between delta G and delta S as delta G is equal to minus T delta S total. So here this delta S, only if it is the total delta S, then we can suggest whether a reaction can be spontaneous or non-spontaneous. So if delta S total is positive, then the reaction will definitely be spontaneous. And if delta S total is negative, then the reaction will be non-spontaneous for sure, because delta G is equal to minus T delta S total. Now coming back to our chemical equilibrium that we are doing. Delta G, now just remember, when it is negative your reaction will be spontaneous. When it is equal to 0, then the reaction is in equilibrium, and when it is greater than 0, then the reaction is non-spontaneous. Now your equilibrium constant can be related to your reaction constant by a relationship which is delta G for any reaction which is trying to attain equilibrium or a reversible process can be given as delta G naught, which is the standard Gibbs free energy. This is the standard Gibbs free energy which talks about the pure states of the compounds, which talks about the standard states of the reactants and the products. It is equal to delta G naught plus RT ln Q. What is your Q? It is the reaction constant, and this is like the ratio of the products of the concentration of the products upon the products of the concentration of the reactants, each raised to their respective stoichiometric coefficient at any point in time. It may not be necessarily at the point of equilibrium. So here at equilibrium what will happen? At equilibrium my delta G will be 0, right? My delta G naught remains as it is. This is the delta G naught for the standard states of the substances that we are taking, plus RT ln of Kc, because at equilibrium my Q is equal to Kc. ठीक है? What happens when Q is less than K? Forward reaction. When Q is less than K, also when Q is greater than K, backward reaction. And when Q is equal to Kc, it is my reaction at equilibrium. So my 0 is equal to delta G naught plus RT ln Kc, which gives us a very important relationship that delta G naught is equal to minus RT ln Kc, or you can write it as delta G naught is equal to minus 2.303 RT log Kc. That is equal to minus 2.303 RT log Kc. And now the cases when delta G naught is less than 0, when delta G naught is less than 0, and the other cases when delta G naught is greater than 0. Remember that when delta G naught will be less than 0, it will be the case only when my Kc is greater than 1. When my Kc is greater than 1. So this means that my Kc will be greater than 1. And when my Kc is greater than 1, then that means my reactant concentration is greater than the product concentration. So this implies and when my delta G is greater than 0, this would mean that Kc is less than 1, which means that the concentration of the products will now be greater than the concentration of the reactants. So this would mean that I am talking about a backward reaction. Okay? And that is how we can then relate the spontaneity. Again the same funda. If you look at the reaction carefully, if your delta G is negative, the reaction is spontaneous, means आगे की तरफ जा रहा है. If your delta G is positive, then the reaction, you won't call it non-spontaneous because this is a reaction in equilibrium. So then the reaction will come back in the backward direction. So less than 0 से वैसे ही आपको याद है delta G is negative, that means the reaction will move forward. And delta G is positive means that the reaction will move backwards. So all these things need to be remembered. Before we move on to the next, sorry?
Delta G and delta G naught.
Yes, here what we are talking about delta G naught is it is in the most standard states. And what are the standard state of the substances when they are attained at a temperature of 298 Kelvin and you have 1 bar atmospheric pressure. So that's like the standard state. And when we are talking about delta G of any reaction, we say that the delta G is equal to 0. That is for the reaction occurring at any temperature. So that is why delta G occurring at any temperature for the reaction to be at equilibrium will be 0, but this delta G naught is not 0. and it can be related to your reaction at equilibrium as minus RT ln of Kc. And this is also used to define, this is actually related to your Q. Alright. Now when your Kc states this delta G turns out to be equal to 0, then again you can say that your reaction is in a state of equilibrium. I think we will take more complicated numericals on it and then you will understand it even better. Just remember for the time being this relationship between Q and K. Now before we move on to the next important principle, which is the Le Chatelier's principle, let us quickly just discuss as to what have we done today, because time is just going to be up. So before we just complete it, what have we done? We've started with chemical equilibrium today. Hardly anything that we've done. We've studied Kc, we've studied Q, and we've studied Kc and Kp, and last we related it to delta G. So just 4 things that we've discussed. The 5th one is still missing, the Le Chatelier's principle, that we can line up even for next time, but I'll just introduce it today before we leave. Okay, the first thing that we do talk about is the chemical equilibrium, and we understand that here we are talking about the rate of the forward reaction to be equal to the rate of the for the chemical reaction, which generally is supposed to be a balanced one. The reaction should be a balanced chemical reaction. Now when we write about the balanced chemical reaction, the law that defines your Kc is your law of chemical equilibrium, where we see that essentially your Kc is equal to, what is it equal to? The product of the concentrations of the products, each raised to their respective stoichiometric coefficient, upon the product of the concentration of the reactants, each raised to their respective stoichiometric coefficient. Then we saw that we can relate it to a reaction quotient, that is Q. Q has a similar expression, with the difference that these all concentrations are the concentrations at equilibrium. For this case, these concentration terms will not be, may or may not be. These concentration terms may or may not be at equilibrium. Alright, then we related it saying that if Q is less than K, if Q is equal to K, and Q is greater than K. We saw it very clearly that if Q is less than K, it will be a forward. Wherever K is greater, wherever K is greater, you will have a forward reaction. If you know one, then the rest of them are known. So please do not confuse yourself by learning all of them up. So if K is greater, it's forward reaction. If K is lesser, it's a backward reaction. Q is equal to K is very easy at equilibrium. Then we did the relationship with Kp. One important thing is like Kp is in terms of pressure, and that pressure is related to your gases only, because we are using the ideal gas law equation here to write down P is equal to C into RT. So your Kp will be equal to Kc into RT to the power delta N. And what is this delta N? This is the change in the number of moles of number of moles of products minus number of moles of reactants, in which you will be considering by and large your gaseous molecules. Okay, then once this Kp is done, we just arrived at the last relationship, that is of our delta G naught, and where we say that delta G is equal to 0 for a reaction at equilibrium, it will be negative for a spontaneous reaction, and it will be positive for a non-spontaneous reaction. But in cases of non-spontaneous reaction here at equilibrium, we mean to say it's a backward reaction. So remember the meaning very clearly, that here the reaction will still occur, because either it will move in this direction or it will come back in the other direction. So delta G is equal to minus 2.303 RT log K. Now if I talk about the graphs of the reaction coming down at equilibrium, because we've been talking of equilibrium all throughout, say if I represent the graph of equilibrium, say here I generally talk of the concentration of, say if I am talking about the concentration of reactants, and then say this is for concentration and this is for time, then I know with time my concentration of the reactants may be high initially, and then it will reduce down with time, right? And if I talk about the, so this is for the concentration of reactants. If I talk about now the concentration of products, what was the concentration of the products initially? It was 0 at the beginning of the reaction. So then it will increase in this form. Alright, so in many of the books you will find that the equilibrium reaction is also, now this is for the increase in the concentration of products, but there comes a time when both reactant and products are in equilibrium state. So the state, this is for a general reaction. For a general reaction, you know that the concentration of reactant will reduce and the concentration of products will increase at a particular time and then become constant at a particular time. So sometimes it is also represented like this, where you have a common line like this. Alright, this will be showing that this is the state where your concentrations may either become equal for the reactants and the products and they have attained some kind of an equilibrium. So this can also be shown for that. So remember this also very clearly. Okay, now there is an important principle. There is an important principle which is called as the Le Chatelier's principle, and that states, now that we've discussed the Kp and Kc very much in detail, we can now move on to something more interesting, which is like very simple also to understand. See, whatever change you will try to do to the reaction will try to oppose it. Okay? If you try to do any kind of a change on your reaction at equilibrium, the reaction is at equilibrium, it will always try to get back to a state of equilibrium only. And in order to do that, whatever change is produced in the reaction will oppose it. This is very popularly known by a principle which is known as the Le Chatelier's principle. Alright, it generally states that the reaction opposes any change that is produced in it. How? Just understand this and we'll start in the next class by discussing about it. Say if you have a reaction, ठीक है, अब ये तो बहुत common चीज़ है that you know that if I increase the concentration of the reactants, what will happen? The concentration of it will move in the forward direction. Why? अब इसको look at it from the Le Chatelier's point of view. If you are increasing the reactants, the reaction will try to reduce the concentration of the reactants. How? By making more products. So it is moving in the forward direction. If I increase now the concentration of the products, then you know the reaction will try to decrease the concentration of the products, और वो कैसे decrease करेगी? By moving in the backward direction. So one thing is very clear that whenever you have a reaction at equilibrium and you try to increase the concentration of either the reactants or the products, it will move accordingly to reduce that effect. ठीक है? One thing is clear. Now we know that if for the forward reaction, delta H for the forward reaction means what? What is delta H? HP minus HR. This you remember. When will it be reactant minus products? When you, yes, in this case, but otherwise if you are given a general reaction like A plus or reactants giving products, and I say delta H will be equal to HP minus HR, in what case will I use the reactant minus product state? When I have the bond energies. You remember? Rusted. Mind has been rusted completely. Please provide some oiling to it. What we did in thermodynamics was, throughout in thermochemistry, wherever we calculated our delta H, it was enthalpy of the products minus enthalpy of the reactants. But I told you, if the bond energy data is provided to you, you will be taking the bond energy of the reactants minus bond energy of the products. Do not forget that. So now coming back to delta H only. I am just talking about the delta H case, and you know that if your delta H is negative, then your reaction is exothermic in nature. ठीक है? अगर मैं बोल रही हूँ that the forward reaction is exothermic, that means delta H forward is negative. Remember that if the forward is negative, it is automatic that the delta H of the backward reaction will be just positive. So if the forward reaction is exothermic, then the backward reaction will be endothermic clearly. ठीक है, अब इस चीज में ये चीज ध्यान से देखना. Now if I increase the temperature, the reaction will try to reduce it. एक्सो में क्या होती है? हीट इवॉल्व होती है तो टेम्परेचर ऊपर जाता है. एंडो में क्या होता है? हीट अब्सॉर्ब होती है एंड टेम्परेचर डिक्रीज हो जाता है. एक्सो में heat is given out. When it is given out, you can feel it, temperature goes up. When heat is absorbed by the system, then in that case you say that the reaction is endothermic and the temperature goes down. So if I am increasing the temperature, the reaction will move in the direction which is endothermic. Get this point? One last thing again. If I am increasing the temperature, the reaction will try to decrease it according to Le Chatelier's principle, because it will oppose whatever I do to the reaction at equilibrium. So if I increase the temperature, the reaction will try to decrease it. How will it decrease it? दो directions है, इस तरफ exo है, इस तरफ endo है. So exo में तो heat और generate होगी, तो it will support me. Increase करा, it will increase it even more. But then it will move in the direction which is endothermic. So if I increase the temperature, then I have to look which direction is endothermic. Then the reaction will proceed in the direction of endothermic reaction. Okay? And now if I decrease the temperature, the reaction will move in the forward direction. Why? Because it is exothermic. Either because I am telling you the data is like will be provided to you. Remember that on increasing temperature, the reaction will move in the direction of endothermic reaction. So whichever way, maybe forward reaction अगर यहाँ पे endothermic होती तो you would have said the reaction will be forward. So for temperature it is not particular that whether it will be forward or backward, so you cannot generalize it. You have to look which side is exo and which side is endo. So when you increase the temperature, the reaction will proceed in the direction of endothermic, and when you decrease it, it will move in the direction of exothermic, because it will just do the opposite of what you're doing. Similarly, if I talk about generally, if I increase the pressure of the reaction, if I want to increase the pressure of the system in which the reaction is occurring, then the reaction will try to reduce the pressure. And how will it reduce? By reducing the number of gaseous molecules. This is the last thing that I'm just throwing towards your side, and from here we'll just carry on in the next class. Alright, remember that the Le Chatelier principle simply states that whatever change we are trying to do to the reaction will always oppose it. Alright, this is something that more than what we decided to do today, but we'll take up more problems next time related to Kp and Kc and move ahead with the Le Chatelier's principle. Alright, so keep studying. All the best.